In this video, we're going to be considering the forces acting on a box as it sits on an inclined plane. This plane is at an angle of theta to the ground, and what we're really interested in is the relationship between the angle theta and the coefficient of friction that exists between the surface of the inclined plane and the bottom of this box. First, let's reduce the box to a dot as we make a free body diagram for it. The forces acting on this box include a weight force downward, a normal force that is perpendicular to the surface, and if the box is not moving, a friction force pointing up the ramp. Of course, even if the box is moving, the free body diagram will look pretty much like this because these are the only forces present. It's how the forces relate to one another in terms of their strength that controls whether or not the box is accelerating down the ramp. On the diagram, I've now put an x and a y axis to show you that both the normal force and the friction force are perpendicular to one another and are lying along these axes. Notice that the weight force does not point along either the x or the y axis, and in order to handle this problem further, we're going to have to use vectors to resolve the weight force into its x and y components. The two yellow vectors that I added are the x and the y components of the weight force once it has been resolved. Notice, if you're careful with keeping track of the angle, that theta is also up here, because if you extend the vector down to make a perpendicular line, the angle that I'm indicating right here is the complement of theta, and therefore in order to make this a 90-degree angle, the angle marked up here as theta must be theta. And we're going to use that to find the magnitudes of this x component and this y component for the weight force in the next slide. Let's add some labels to make these forces a little bit clearer. So the normal force we can represent as F sub n. The friction force is F sub F. And we haven't said yet whether we're dealing with static or kinetic friction. We will do that momentarily. And the weight force is F sub W. We were just talking about resolving the weight force into the two pieces F W x, which is along the x-axis, and F W y. We're going to find the components of our weight vector by resolving it, that is to say projecting it against the two axes, x and y. So we can find the y component, which is this yellow arrow, by saying that Fwy must be equal to the length of the weight vector, Fw, multiplied by the cosine of theta, because it's adjacent to that angle. And by symmetry then, we can say that Fw in the x direction must be Fw times the sine of theta. Okay, so if that box is not sliding, then all forces up the ramp must be matching the forces down the ramp. That is to say, since we've got the force pointing down the ramp due to gravity in the x direction, Fwx is what we just called it, then the force up the ramp, which is that due to friction, in this case if the box is not sliding at all, then it's static friction, must be matching that. So Ff must equal Fwx. Since the box isn't levitating above the ramp and it's not sinking into the ramp, then the normal force upward must be balanced by the component of the weight force along that y-axis as well. So far we've established that because the forces are balanced, these equations must be true. We also have an expression for this and this that involve the weight force, and we can express the friction force and the normal force maybe as something else that will help us to combine all of this information to get a relationship between theta, the angle of incline, and the static coefficient of friction. Previously we said that Fwx could be rewritten as Fw times the sine of the angle of incline, and so that means that we can re-express this equation in the following form, also knowing that anytime we see a weight, we can express that as the mass times gravity. We can write this as mass times 9.8 times sine theta equals Ff. Now it's time to remember that any time that we see a friction force can be rewritten in terms of the normal force and the coefficient of friction. So mg sine theta equals mu times Fn, and I'm leaving off the subscript right now, but we could say that that is mu static if the box isn't moving anywhere. Using a similar system, we're going to take the y component of the weight force, equate that to the normal force as we've done, plug in what we know about it in terms of the angle, and find out that Fn, the normal force, is related to the angle as well. Of course, we can also say that this is mg cos theta, and now we can use this whole expression and substitute it in to what we had on the previous page, which was that mg sine theta is equal to mu times Fn. So on the next slide, I'm going to be substituting this whole expression into this one for Fn. Okay, so here we have mg cosine theta being plugged in for Fn. Notice that now mg will divide out of both sides, and if we solve this, we find that mu is equal to sine theta over cosine theta, which is just the tangent of theta. And that's the relationship between the coefficient of friction and the angle of incline. In the case where a box is not moving, then we're talking about the coefficient of static friction. And in the case where a box is sliding at a constant velocity, then that's the coefficient of kinetic friction.